Chapter 7 is applications of integrals. One of the most common applications of integration is finding area between two curves. We've already seen the definite integral as the area under a certain curve. Now we're just going to use integrals to model areas of more complex regions. Check out this first example. I made the picture bigger for you. We've been asked to find the area of this region that's been shaded for us. It's the area between the curve y equals secant squared of x and y equals sine of x. We've been asked to have a left limit of x equals 0 and a right hand boundary of x equals pi over 4. So they've colored in this region for us. It's our job to find the area. So notice that we could find the area by pretending this was all colored in. We could find the area under the secant squared curve, right? And then subtract away the area that's underneath the sine curve. So that's exactly what we're going to do. So this is my plan. I'm going to find the area underneath the secant squared curve between 0 and pi over 4. And I'm going to subtract away the area underneath the sine curve between x equals 0 and x equals pi over 4. So a couple things to notice. If this is an integral that I'm writing with respect to x, with respect to x, that means I'm using dx. That means my integrand has to be a function of x. And it means that these limits, the lower limit and the upper limit, are both x values. Specifically, the lower limit of my integral is the leftmost x of the shaded region, and the upper limit is the rightmost x that we find in the shaded region. You are likely to decide as you move forward that it's too much of a pain in the rear to write two separate integrals, because remember that we can separate integrals at subtraction signs, so we can recombine integrals at subtraction signs too. So that's what I have at the top is the same as what I've written here, just probably what you will get in the habit of writing, which is the integral from 0 to pi over 4 of secant squared of x minus sine of x. I can find this result by getting an antiderivative for secant squared x minus sine of x. That's tangent of x plus cosine x. I'm going to evaluate that from 0 to pi over 4. That gives me tangent of pi over 4 plus cosine of pi over 4 minus the quantity tangent of 0 plus cosine of 0, which I didn't write in, so I'll write it in right now. Tangent of pi over 4 is 1 plus cosine of pi over 4 is radical 2 over 2 minus tangent of 0 is 0. Cosine of 0 is 1. Recall in a free response question, you would not be required to do this simplification, but we'll do it here so we can check our answer in the back of the book. So this is 1 plus radical 2 over 2 minus 1. So final answer, square root of 2 over 2. So come back to this picture here. So we can just notice before we move on to the next example, this works, that integral that I wrote works as a model for this area because the upper boundary of this blue shaded region is, if I trace along it, the whole time I was tracing along this curve, y equals secant squared of x. And if I traced along the bottom boundary of this curve, the whole time that I was tracing that, I was tracing on y equals sine of x. So if I were going to think about this region as infinitely many, infinitely thin rectangles, here is an example of one infinitely thin rectangle. Its width is a very, 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 very small change in x, which is dx. It's infinitely small. It's close to 0. It's really close to 0. And the height of that rectangle, the thing I'm going to multiply that very tiny width by is this distance. So however tall that line segment is. So notice that that line segment is vertical, which means if I was going to figure out the distance between that top point and this bottom point, I would just have to subtract the y values. Well, I know a formula for the y values, and that's how I get that expression that's inside my integral, which is secant squared of x minus sine of x. That's an expression for the vertical distance across this blue region, and I'm going to multiply by a very teeny tiny change in x to get my height times width for infinitely many rectangles between the x limits of 0 and pi over 4. So I'm getting there a little bit early, but if you'll notice down at the bottom of the page, I've written an expression that I hope is helpful to you. It's not so much a formula because you're going to do this so much. It's not going to feel like a formula. But if I want to find the area between two curves, as long as there's only one curve that's ever on top, and there's only one curve that's ever the bottom boundary of the region, I'm going to integrate from left to right of the top curve minus the bottom curve.